Well, hello, my name's Billy Martin. I'm a principal engineer for Cessna Aircraft Company in the area of electromagnetics. I've worked for Cessna for 23 years, and in addition to my duties as a principal engineer, I also run an EME lab for Cessna, and I'm the chairman of the national committee that writes all the Lightning standards for aircraft from a Boeing 787 down to a Cessna 172. So what we're going to talk about this afternoon is direct effects of lightning, the requirements that the FAA places on us, and also how we do design aspects and protect against those. So let's talk a little bit about lightning. Lightning, basically, direct effects deals with any physical damage associated with the aircraft as a result of a direct attachment for lightning. And we think a lot about that as being the points where lightning attaches to the airplane, as well as that where it exits at. But there's a lot of other stuff that goes on in between. How does lightning get from the point of attachment through the aircraft and exiting out? So direct effects includes not only those attachment detachment points, but any sort of damage associated with tearing, bending, vaporizing, various paths through the aircraft, and also possible damage to electrical and electronic and mechanical systems. So what exactly is lightning? Okay, well, lightning is a high voltage, high current, self-sustaining device. What that means is the high voltage is that lightning contains a certain amount of power in it. So the high voltage is that power. High current is the ability that lightning has to deliver that power. So even though I have a light switch in my room, the light doesn't come on till I close the circuit and current flows through the light bulb. So high current is the ability to deliver that high power. And self-sustaining means that it doesn't stop till the good Lord says so. And there is nothing that the pilot can do if lightning attaches itself to the airplane. Can't reach over there, turn a switch off, can't pull a circuit breaker, can't do anything but hope engineers like me and maintenance people like you have maintained the aircraft in a manner that makes it safe against those threats. So this pictorial right here is basically a picture of an aircraft being encapsulated in a high electrical field. It's called equipotential lines. And if you look at the lines on the outside, they're fairly even. But as the aircraft extremities are approached by these lines, it compresses. What that means is the electrical field is enhanced in those areas. And when it becomes enhanced to a certain level, it starts streamering. It's called corona effect. And you get these little streamers propagating away from the aircraft looking for some place to go. So the lightning interaction with an aircraft occurs when that airplane's surrounded by these electrical fields. The fields are enhanced in the areas like the wingtips, the radomes, that sort of stuff. And the air around the aircraft starts to ionize. Okay? And you get ionization, corona effects. If sufficiently intense, if that corona effect's sufficiently intense, then streamers start to occur on the extremities of the airplane. They'll propagate away from the aircraft, and if there's a channel, a lightning channel already in the air, okay, created by this high voltage phenomena, then the streamers from the aircraft can contact what's called a step leader. Probably 99% or 95%, I don't know, pick a number in the 90s, of aircraft are struck by lightning. It's what we called intercepted lightning. What that means is that a channel is already formed. And if you look at lightning in the air, hopefully from inside, don't stand out in it. But if you look at lightning in the air, you'll see that it propagates in what's called a step leader propagation. Never goes straight. If you look at it as it propagates across the sky, it steps. That step leader is already forming when the aircraft flies into that thunderstorm area. If the air is sufficiently ionized, you get streamers. Then those streamers from the aircraft intercept the step leader, becoming part of that channel. That's what we mean by intercepted lightning. You can also have what's called triggered lightning. An aircraft flies into an electrical field and it creates a streamer effect. Now, typically that happens in intra-cloud lightning. an airplane flies into a high intense thunderstorm and it triggers lightning effects. But typically airplanes are struck by what we call intercepted lightning. Once within that channel, that airplane again can't do anything, okay, can't escape. It's part of that lightning channel. And when that channel propagates down either to the ground or to another charge center in a cloud, then you close that circuit, and just like when that light bulb lightens up, so does that airplane, okay? So it's critical to have a low impedance path to ground through the airplane structure to protect against what is considerably a high amount of current. Now we test to 200,000 amperes of current, but there have been current returns measured in excess of 400,000 amps on things like towers. And we've had damage to airplanes that far exceed the level that we would expect to see if we saw a 200,000 amp. When we go into the laboratory, we cannot replicate that damage based upon 200,000 amps. Now again, this is a pictorial of a step leader, an intercepted type of lightning. You have a cloud center here, and what happens is all those electrons start rubbing up against one another, getting all excited, okay? And part of those electrons rub off onto an atom, and it becomes negatively ionized, and therefore, because it picked up an electron, it gets heavier, and it floats to the bottom of the cloud. Those that lost an electron, as the cloud convection activity occurs, pushes those electrons up to the top of the cloud. So now what do I have? I have a battery, positive and negative. If that battery becomes strong enough, i.e. the voltage is sufficient, you get a step leader propagating away from that charge center. The aircraft starts approaching that step leader, and if it is within a sufficiently high enough ionized airstream, streamers start propagating away from the airplane, and this step leader connects to what we call a dart leader from the aircraft. At that point, the airplane is part of that channel, and there's nothing the pilot can do. At this point, too, this is strictly a high voltage phenomena at this point, too, because again, I haven't turned that switch. I haven't closed the switch to the light. I haven't closed the return path. So it's still a high voltage phenomenon. But once that channel propagates down to the ground, I've completed that circuit flow or circuit, and now high amounts of current can discharge back through that channel into the aircraft. And you see the same thing in life. When you watch lightning propagating through the sky, you'll see it come down, it'll hit the ground, and you'll see that large flash occur as that return stroke goes back up into the clouds. That large flash, in which creates not only high amounts of current flow, but also thunder due to the collapse and the vacuum created by that large amount of plasma flow, and creates a thundercraft. That shockwave effect also hits the airplane. So, now we know how airplanes interact with lightning. How do we do to protect it? Okay. Well, the first thing we do is we zone the airplane. And the aircraft is zoned in probability for direct attachment. In other words, how probable is lightning to attach to any one particular area on the aircraft? And if you think back to that picture that we showed with the airplane in the electrical field, you see when the intensity of those fields were right around the extremities of the aircraft. So we'd expect that those particular areas would have a higher probability of lightning attaching to them than other areas of the airplane, and that's exactly right. So we zone the airplane. Zone 1A is considered to be zones where there is a high probability of direct attachment for lightning. That's around the nose, the wing tips, the horizontal stabilizer tips. Zone 1B is the area where lightning is likely to detach. That's along the trailing edges of those areas of the wing tips, the horizontal stabilizers, possibly the rudder. Zone 1C is kind of what we call a transition zone, typically in the nose of the airplane. If you have wing-mounted engines, you can also have that transition zones there. But fortunately at Cessna, we put engines where they're supposed to be on the fuselage. Okay? But what we have is a direct attachment. The airplane continues to move forward, though the lightning channel is stationary. And a lightning channel has mass associated with it. It's a plasma. So the airplane is moving forward while the lightning channel is propagating down to the ground. If I'm flying at 10,000 feet, and there's a speed limit at 250 knots at 10,000 feet, that lightning channel will move 2.3 meters, or the aircraft will move 2.3 meters in the time that it takes for that channel to propagate to the ground and then the return stroke to occur back through the airplane. So what that means is it can sweep backwards on the surface of the aircraft. Now, it's kind of hard to imagine that because the channel is stationary, but the airplane is not. So really, the channel's staying here and the airplane is moving forward. Unless you're in a helicopter, the return stroke can occur at the same point of attachment. Now, for an airplane, it's moving forward. So we have a transition zone that goes from the nose, 1.3 meters, which would be 5,000 feet, and then another transition that goes from 1.3 meters to 2.6, which would cover 10,000 feet. Why did we choose 10,000 feet? Primarily because it made it easier for us as a committee because there's a speed limit. If I take a Citation 10, flies a lot faster than a 500 does. But they both have to fly at a certain rate of speed at 10,000 feet. And the majority of strikes to airplanes occur in and around airports, in the clouds, at or below 10,000 feet. Why is that? We have to land and take off. If we're smart, we fly around thunderstorms and not through them. But a lot of times when we're taking off and landing, we will progress through thunderstorms and you take lightning strikes. Also occurs right around freezing, but that's another physics question. This is a picture of a citation in which we've zoned the airplane. Again, this first portion is zone 1A. The transition zone after that's 1C. And then there's another zone right here, which I didn't really talk about last time, but it's called a zone 2A, which is called a swept stroke zone. But it's exactly the same phenomena that occurs at the transition zone. The lightning channel is stationary, but the airplane is moving forward. That stationary channel gets pushed back physically because it has a mass due to the wind loads on it. It's no different than if you're taking a flame off of a match and you blow on it. That flame has mass too. You blow on it, what happens? You make it go in a direction. That same thing happens with lightning. The airplane's moving forward, there's a wind load on it, and it pushes back until such time the magnetic field can't hold anymore, and it comes up off the airplane moves under it, the channel attaches again. And it will literally sweep back across the airframe till it reaches a point where it hangs on, and now the channel's coming down and the attachment and detachment points are exactly the same location. So this is called a swept stroke zone. Now you notice we have a lot of areas in here where there is no color. That's called a zone 3, and the probability of attachment of lightning in zone 3 areas is relatively remote. It's not zero, but it's small. Now why is that? Okay, again, think back to that picture that showed those lines so close together and it was enveloped around the aircraft. There's nothing in here that can cause the electrical field to be enhanced. It's fairly flat, so there's no enhancement associated with it. That doesn't mean it doesn't get struck, because there are things like air brakes going on in here, your flaps can be up or down, your ailerons can be moving, so there can be sharp points and you can have a strike to those areas. But typically if you take a strike in those areas, the striking distance, in other words, the length or distance the lightning has to travel in order to attach to something, is relatively small. There's another thing about lightning. If it has to go a really long distance to get someplace, it's kind of when it gets there, okay? So it has to take a lot of power to travel that distance. Whereas in a zone 3 area, if I'm getting struck in a zone 3 area, that's an intracloud. In other words, I have a charge center in this portion of the cloud, a charge center here, and the airplane flies in between it. So the striking distance is relatively small. So therefore the amplitude of the current is relatively small. Now we do take strikes in the wings, but the damage is relatively light because of the amplitude. So we zone those areas as zone 3 of a low probability of attachment. We don't put as much protection in there, but we also put stuff in there that's really important. It's called fuel. We put it in there because it's a nice, convenient place to place it, but also it doesn't get struck by lightning very much. And to go back to that, we try to keep fuel out of these areas. So that's how we zone the airplane. So now we know how the aircraft interacts with lightning. We know how we predict the probability of attachment. So we know pretty much where lightning's going to attach at on our aircraft. So now we can get into the scheme of how do we protect it. How do we protect structures? Well, I'm in the safety business. We in aviation are in the safety business. It's critical that we design our aircraft such that people can travel from point A to point B and do it safely. And we have a remarkable record in that. So the primary concern in regard to lightning is the same concern we have as in regard to icing, in wind shear, in turbulence, in any other environmental effect. It's safety. So if there's no safety hazard, I'm probably not going to protect it. If I have the tail feathers on a 525 airplane that has static wick and it's closeout fairing, that fairing is not protected against lightning. So you say, well, why not? Okay. Well, number one, if it blows it off, it's no safety effect. Now, it's an economic question, okay, but it's not a safety effect. And so does it make sense to drive that economics into every one of those parts on the off chance, and then we don't get struck by lightning all that often because we're smart enough to fly around it, on the off chance that we will take a strike such that it'll blow that off? So do I drive that cost into every airplane? So there's an economic trade-off. And in all engineering is a trade-off. We don't trade against safety, but we do trade off against economics. So it's a trade-off between the standpoint of protection and the cost of repair. The primary protection scheme for lightning and mechanical structures is contained in the Rule 25581. And I have a copy of it here. And basically it says the airplane must be protected against catastrophic failure conditions. Good thing. We don't want to make a hole in the ground if we get struck by lightning. We can do that for metallic components by electrically bonding those components together to present a low impedance path for current to flow from the attachment point through the structure of the airplane and out the detachment point. We electrically bond things together and we design it so that it will not endanger the airplane. So that includes things like fuel, okay? Though that's covered under a different rule, it gets kind of gray in those areas between 581 and 954. For non-metallic components, for composite structures, okay, it's a little bit different. Metallic structures are inherently immune against lightning. They're very low resistivity. They can handle large amounts of current flow. Composite structures are not. So we have a different means of protecting. First off, we try to minimize the effect of the strike. Notice it doesn't say eliminate the effect. It says minimize it. If you take a lightning strike, as we'll see here in a little while, on a composite structure, it will have an effect. All right? And it will on metal too. It's just minimized. And divert the current as to not to endanger the airplane. And that can be done in several different ways. Right? But we don't only think about where we exit, okay, entry, exit, but we also have to protect all points in between. There are three areas that must be protected from an airplane. The entry point, as we talked about, the zone 1A, 1C, 1B area, that's the entry points. The exit points where the lightning detaches from the aircraft, that's those 1B and 2B areas, okay? And the conductive current paths, which are what's called the zone 3. And though I mentioned the zone 3 on the wings, the zone 3 also underlies all other zones. It underlines the 1A, the 1 or the 2A and the 1A area. So current must flow through the aircraft. Now that's easy to imagine whenever I take a strike on a wingtip and it exits out that same wingtip. I can see where the current flows into that wingtip, exits straight out. But what about if a current attaches or lightning attaches on one wingtip and then exits out the other? Now all that current had to flow through the surface and interconnecting hardware inside the wing, like the hydraulic lines, like the fuel lines. So now current has to go through that structure. Or if I attach on the nose and detach off the horizontal stabilizer, elevator. Up on the elevators, we typically have moving parts to control flight control surface, and we typically have hinges that allow those parts to move. Well, those hinges have Teflon bearings in them because we don't want to wear them out, right? Bearings that are electrically isolated. So we put bonding straps across there. So that current has to flow all the way through the structure of the airplane, internally as well as externally, and exit out that part. So that means all that current has to go through those hinges. And if we don't design it properly, it won't go through those bonding straps or hinges. It'll arc somewhere and you could damage the hinge to where it would freeze, or you'd cause a lot more damage on some trim tab or something where it'd lock up, or physically blow a large enough hole in it that you'd get asymmetrical control surfaces. Which I'm not an aero guy, but that just sounds bad. So, metal structures. Metal structures are naturally resistive to lightning. It's naturally resistive to high amounts of current flow. That's why we make bus bars out of copper. It's very low conductivity. Why we carry current on copper wire instead of like on your spark plug sometimes made out of carbon fiber, right? Because we want that low resistivity. We don't want to drop a bunch of voltage in there, and it can handle that current flow. So it's naturally resistance due to the conductivity of that. So the main danger to metal structures is not the initial attachment point or even the detachment. It's long duration current flow. If I have a lightning strike will typically last anywhere between 1 to 1.5 to 2 seconds. Now during that time you can have multiple strokes occurring, and we'll talk about that more in a different lecture in indirect effects. But you can also have what's called long dwell or continuing current. And that looks just like when you look at it in tower measurements or when you make measurements on airplanes. It looks just like a DC battery current. And within about, we typically test for, say, a 50 millisecond. We can have close to 25 to 30 coulombs of current flow. Now that's 1 amp per second, okay? So what that means is that a whole bunch of power goes through a very small area in a very short period of time. And that long duration current flow, and you may not think 40 or 50 or 60 milliseconds is a very long duration current flow, but it is if you're driving 900,000 amps of DC current through it. So what happens is that long duration melts metal surfaces. But it not only melts the metal skin, it can melt bonding straps. It can melt hydraulic lines. It can melt other attachment points that then cause other issues on the airplane. So long duration dwell times on bonding straps create a tremendous amount of problems on aircraft unless they're designed and maintained properly. Long duration current flows on skins, say fuel skins, if they're not designed thick enough, can burn through it. If there's fuel vapor present, can cause a fuel ignition. So long duration current flow is a problem. So for that, we have to design sufficient current paths for that lightning current. So anytime you install electrical equipment on the outside of the airplane, it must be bonded properly. But it's more than just a DC bond. And I know we use a DC meter to measure that bond because we really have no other useful tool that enables us to do that. But just because a particular part measures 2.5 milliohms and we measure it on I put a light bulb or a light fixture on a wingtip, and I measure from the skin to the structure, and I measure 2.5 milliohms, and I say, oh, I'm good, I'm ready, I'm done. The problem is I can take a 20 gauge wire and hook up a little short piece of 20 gauge wire to a light fixture and ground it to ground and make that measurement, and I'm 2.5 milliohms and I'm good. Problem is that little 22 gauge wire is no more than a fuse, all right? And when current flows through it, that small amount of gauge wire can't stand it, it explodes. So the key to good electrical bonding is not just the number, it's how you install things, the current density. The larger the contact area, the better the current density or lower the current density is, and the better protection you'll get. Because now I'm driving current over a large area, not just a small area. So we want to make sure that we have good external grounding points, and the larger that surface area can be, the better it is. Now we have to think about corrosion when you think about electrical bonding, because I don't want to clean all the primer off, leave that exposed, because it'll be good when I do it. 5 days later, it'll be corroded. So I have to think about it, okay? So I want to make sure that I have a good, sufficient path to ground. In the case of composite structures, it is critical, and we have to design it into structure. For a metal structure, I just make sure I've cleaned that surface off properly. I have a sufficient bond path. I got enough fasteners going through there, and it can handle a current flow. But for composite structures, it's a lot different. So we design for composite structures. This is a bullet fairing off, I think it's either a CJ3 or a CJ4. I'm not quite sure. I think it's a CJ3. Anyway, this is the fairing, and this is carbon fiber right here, and then there's a metal fairing that goes all the way around this bullet area. Now, every time I tell project engineers they have to put these metal straps and stuff in there to bond lights and fixtures to the aircraft structure because the composite's not sufficient, then I hear all about this weight and we can't do this and all of that. But there's a reason why we do it. On the CJ3, this bullet fairing has two different lights on it, one at the very far back and one at the top. This shows the light fixture in the tail end, in which we put a recognition light, and the wire bundle is routed along this path so that the wire is protected and the light provides this doubler provides a nice current path. If lightning strikes that light, it can go through the screws and into that doubler and back to the aircraft. It reduces the current density in any one location. Now this is after a lightning strike on that light. Now this happened to a CJ3. The guy took a large amplitude lightning strike. It actually burned holes in the metal structure all the way back, and it exited out the tail. When the guy landed, avionics equipment didn't blink. He took a lightning strike. Once he could see again, there was a little bright flash there. But the avionics equipment didn't even blink. Everything was fine. He thought, hey, everything's good to go. He landed the airplane, got out, walked around the back, and the light was literally hanging down from the wire and had burnt this doubler completely out. However, the light was still working, okay? Now, if that doubler had not been in there when it exited out, it would attach to that wiring. If it attached to the wiring, it would have exploded the wiring, number one. Explosion and airplanes don't go well together, by the way. It would have exploded that wire, got onto the 28-volt line, and that cockpit probably would have went black, as well as other things happening. As it was, yeah, we burned that area out because it was a long duration, high amplitude strike. But because that doubler was there, we protected the airplane. And by providing that electrical bond and distribution of that current, guy landed the airplane fine. We replaced the part, okay, but we minimized the effect of the strike. So that's for light structures, pitot tubes, anything like that mounted on composite structures. So what about control surfaces? Okay, again, control surfaces are very important to the safety of the airplane, so we pay a lot of attention to them. And most control surfaces have multiple hinge points across there. And if you go look at our airplanes, you'll see that there's bonding straps across multiple hinges. Not across every one of them, So let's say I have a short aileron, it's got 3 hinges, but they're only 1.5 feet apart. We probably put one on this side, one on this side, and we call it good. Right? Where if you take the elevator on a Citation 10, they may be 4 of them across there because of the distances across there. But we put multiple bonding straps across the hinges of our control surfaces primarily for 2 reasons. The first one is it provides redundant protection. So if I happen to pinch one, if I happen to break one in between the time that I do maintenance on the airplane, I still have protection. But the primary reason that we do it is to reduce the current density by dividing that current up. So when the current comes through the structure of the airplane and it's looking to get out the end of it, then it sees multiple paths. And it's just like water, okay? When you flow water down and you divide it, you see water flowing through multiple paths. If you look at waterfalls or whatever, if there's obstructions in the path of the current flow, you see the water dividing and moving. Well, when that happens, we reduce the volume of the water going in any one location, right? Same thing happens with electrical current flow. By reducing the amount of current density across any one strap, we reduce the amount of heating that occurs across that strap, as well as the amount of power that it has to handle. So by reducing that current density, we minimize the damage going through those control surfaces, and the likelihood of them freezing, arcing, and welding together is minimized. Okay, and this just shows an example of the bonding strap that I'm talking about. And there's a couple of key points right here that we need to think about. First one is the size of the bonding strap. Okay, and you notice it's fairly substantial. If you don't make that bonding strap sufficiently large enough to carry large amounts of current, it becomes a fuse again. Okay, so, and the other second point is the electrical bonding aspect of the bonding strap. You have to ensure that that connection is terminated properly to ground, because this is the highest resistive point on the hose strap, this point and that point, as we join them together. So we drive that resistance up. Ohm said current times resistance creates voltage, and voltage ain't our friend. It causes arcing, it causes explosions. So there's 2 ways to bond that. Clean that surface off, you put it together, and you tighten it down, you put sealant over the top of it, seal moisture out. Or a better way to do it is to clean that surface off, use conductive sealant underneath it, press it together, seal the moisture out of it while you still bond it, and you'll create that good electrical current flow. It's critical, because here's what happens if, number 1, it's not bonded properly, and number 2, it's not sized properly. These are bonding straps that were taken off an Embraer 145 that landed in Hartford, Connecticut back in 2002. And it's on the horizontal stabilizer of the 145. It's very similar to Citation 10. It has an actuator in there, moves the horizontal stabilizers up and down. These bonding straps were not sized properly, and they weren't terminated properly. And when current went through them, high duration current flow went through it, it literally melted them. And the current then jumped, because lightning's going to flow through that aircraft. You either design the current path and make it go where you want it to, or it will choose its own path. In this particular case, it arced to a control cable, burnt the control cable in half, and they made an extremely hard landing in Hartford. If it would have attached to the other one as well, they probably would have lost the airplane. So that's control surfaces bonding. What about engines? Engines are isolated, right? We put them out there on these big old banana clips and tie them to the airplanes, but they have a tendency to move a lot, so we put them on isolator pads. It's critical that we electrically bond those engines to the airframe structure for multiple reasons. Number 1, we got fuel going through there. Number 2, we typically have what's called a FADEC, full authority engine control, and we want to minimize that resistance. So we use bonding straps across each one of our isolator mounts. And those bonding straps have to be sized properly, okay, and bonded into the interfaces. And it's also critical that we bond all of the electrical connectors through the firewall, because we want to make that firewall works not only for fire, but it also works for electromagnetics. If I create a large amount of current flow on the wire bundles, because I take a lightning strike on the engine exiting out the engine, a lot of current flows on those wire bundles. When it hits that metal wall, if we've done a good job of electrically bonding right there, then that current goes into the structure of the airplane, diffuses without getting onto the wires and carrying into the structure or into our aircraft. So electrical bonding at the interface wall is critical. And that's true too for all wire bundles as we move from one structure to the other. And we'll talk about that in the HERF and in the indirect effects. So you'll have to come back and listen to me again. Anyway, this is a bonding strap on an engine isolator as we move from the engine mount to the engine itself. And you notice the size of that strap and also the thickness, okay? It's very short and it's very wide. That reduces the inductance and the resistance, so current flow going across there minimizes the voltage. Also, that engine's sitting out there by itself, vibrating along. We have lots of sensors and stuff on there that even if we're not even talking about lightning, it is critical that we bond that engine properly to structure, because a lot of those sensors are electrically isolated or bonded on the engine, and then we read the energy or whatever from that sensor, the signal in the cockpit. And if we don't bond those things together and there's a large difference of potential, we get errors. So it's critical to bond the engine regardless, okay, of lightning, just for the good operation of the sensors and the electronics on the engine. So this is what happens when electrical current flows through structures where it's not designed for it. This is a push rod and some sort of control cable in which electrical current we didn't design the airframe properly. The current paths weren't designed, so it went through the control rods. They were not designed for current flow either, and you can see the magnetic field effect crush those rods. So we really want to design paths, or lightning will find its own way. If we don't design it properly, this is a successful landing, by the way. People walked away from it. But what happened here was the guy didn't design a current path through the elevator properly. It then attached on this control and blew the guy apart. And they lost all pitch trim control, and they landed the aircraft without pitch control. So we have to design current paths. But also, if we have things on the outside, like pitot tubes, like antennas, things like that, it's also critical to design the electrical current flow. Now, I can't stop it from attaching, but I can sure divert the current and minimize its effect. So when I put things on our airplanes, we do it with a doubler on the outside, and then we attach it with multiple screws, so that anytime current attaches here, it doesn't just go through one of them. It goes through all of them at the same time. That reduces the current density, minimizes the heating effects, and reduces damage. Okay? So that's how we do protection for metal structures, for control surfaces when we're looking at conductive currents. All of that I've talked about is primarily metal, with the exception of that CJ3 composite fairing, but the point was the metal doubler inside of it. So how do I protect things that I can't make into metal? How do I protect things that are, in fact, electromagnetic windows, like radomes? Okay? Well, we do it in two different manners. First, we do PStatic Paint. Now, the application of PStatic Paint is kind of a black art, okay? The way that paint works is it's loaded with a carbon fiber material. You spray it onto a surface. That carbon fiber material flows out evenly on that surface, providing a very high resistive but yet conductive path to bleed electrostatic charge off. Now, electrostatic or PStatic is a different type of phenomena, than what lightning is. It's like when you rub your foot. A perfect example is when you go to the grocery store and they've just waxed the floor, and you're walking across there and you have dirt on your floor and you reach and touch and grab that handle and it shocks you. That's about 6,000 volts on your fingertip. If it had a lot of current behind it, you'd be sitting on the floor wondering what happened. It doesn't have. It creates an arc and it sits there and goes, and that builds up in your comm, and you can lose navigational comm stuff. So we have to bleed that static off. So I have this large piece of non-conductive surface out there that gets hammered all the time with ice particles, rain, whatever, and it builds that charge up. So we bleed it off by PStatic. And then we protect it from lightning from what's called diverter strips. Now, PStatic, in order to function properly, the paint must be, number one, mixed properly, number two, applied properly, and number three, cured properly. If you do not do any one of those things, guess what? It will not work properly, okay? So the paint must be applied also directly to a metal surface to bleed it off. In the case of the Citation jets, where we have that little metal skirt on the backside, we sand the part of that down, exposing that metal, and we spray the PStatic paint directly on top of it, thereby providing a path to ground. Remember, just like in lightning, current doesn't flow till that path is completed. In this particular case, we have to make sure that that PStatic path has a bleed path to ground. If we spray it on top of primer, if we spray it on top of sanding surface or whatever, if it's not directly on top of that metal, it will not bleed it off. So it must be applied properly. The other thing is the maintenance manual calls that out. There is a repair criteria within the maintenance manual in Chapter 53 that tells you how to properly apply that PStatic paint. And it is critical. Mix it, apply it, cure it properly. This just shows the 525 radome. You can see where the metal rivets are in the backside, and there's a skirt that goes around here. When you apply that, you can either apply directly over those rivets, because this is from a factory picture, so you can apply it straight over those rivets, or you can sand that skirt down a little bit. Either way, it has to be applied evenly around the circumference of the radome to the metal structure, and then the metal structure is applied to the frame, and the frame is then attached by attachment hardware to the structure of the airplane. Let's go back to that second. For a Citation 10, a 680, all you have is these rivets around the bottom side of it that are going into the frame. So it's critical that those are cleaned and the PStatic paint applied directly on top of it. So segmented diverter strips. How do we protect our radomes from lightning? Because I can't make the radome out of metal. I could, okay, but it wouldn't work real well. All right. So how do I prevent lightning from puncturing through that composite and attaching to the metal antenna underneath it? I use diverter strips. Now, most of you have looked on commercial airplanes. You see these big giant metal bars on the outside of the radome, 737, MD-80, whatever. Those big bus bars right there are diverter strips also. The problem with those guys, and they work very well, by the way, the problem with those guys is I can't move them into the front of the radar, because if I do, it affects the performance of the radome. It's called transmissivity. How well does energy move through the radome and move back into the radar? When I put big chunks of metal in front of it, it attenuates the signal. So what we use is a segmented diverter strip, and they worked a little bit different than solid bars. Where solid bar, lightning directly attaches to the surface of the bar, and it flows directly on the surface of the bar. So therefore, if I have long durations, I melt them, I do all of these things. Segmented diverters work a little bit differently. There's a bunch of small segments with little gaps in between there, and they act like capacitors. And when the electrical field is intense enough, remember back to that picture way back at the beginning, right around the nose, you get enhancement of the electrical field. If it's sufficient enough, those segments start streamering. And when they streamer, they bridge that gap. They ionize. So when a lightning channel comes down, it flows in an ionized path, okay? Again, in order to work, the airflow must go over the top of the segment. If I paint over the top of those segments, I prevent them from ionizing and they will not work. So it is critical that you don't paint or put anything else over the top of the segments. They have to be exposed. And it's also critical that they're properly electrically bonded to the frame of the radome and the radome bonded to structure. So I have a low impedance path from that channel through that attachment screw into the structure of the airplane. And this shows exactly what I'm talking about. If you look, you can see each one of those small segments lighting up as the air above those segments are ionized and the current flows over the top of it and into the structure. And this shows a nice picture of how that air and that lightning channel is ionized back to the structure of the airplane. So that's radomes. So let's talk a little bit about composites. In some cases, I have composites all over the airplane. Fairings on the 750 are made out of composites, control surfaces, all of them. Okay? So, and in my opinion, in a few years, everyone will be making composite structure airplanes. So this problem's not going away. Okay? Today, we minimize that. We only have them in engine nacelles, fairings, control surfaces. We have yet to build a fuselage or wing out of that. But the 787 is a composite structure airplane. Once that technology is propagated through industry, a lot of people will be doing it. So let's learn about them now. But unlike composite or unlike metal structures, composites are not inherently immune to electrical current flow. They're about 1/1000th times as conductive as aluminum. So if I have 1 amp of current flowing through aluminum, I get 1 volt. Let's say it's 1 ohm. But if I have that same amount of current flowing through a composite structure, I get 1,000 volts. Okay? So because it's so much more resistive, we have to design things to minimize those. So composite structures have lots of advantages. Okay? They can be made in very complex shapes. If you look at the fairings on the 750, they're made in very complex shapes. They can be made repeatably. Okay, I make them, I push them into a tool. They reduce the amount of labor intensity, so there's cost savings associated with that. There's weight savings. Supposedly I can make them lighter, I can make them stronger, I can make them in more complex shapes than I can in metal. So they have lots of advantages, plus they don't corrode. But when it comes to lightning, just like in any other engineering there's trade-offs. And with composite structures, when I start thinking about lightning, it costs me money. I have to add different materials in there. And when I add different materials, it costs me weight. Now, the protection scheme for composite structures, okay, is basically try to make them like metal. Okay. So whether it's non-conductive or conductive, we try to make that surface like metal. And these are the various schemes that have been used throughout the years to try to convert that composite structure into a more conductive surface. We typically, most industry uses these last two, an expanded metal foil or what we call a carbon fiber composite with ALS, interwoven wires. This is the expanded metal foil. This is aluminum, but you can also get it in copper, bronze. The pink portion of it's what's called a pre-preg. You lay this up directly in the mold with the carbon fiber and it becomes the outer layer of that material. This is ALS material. You look, this is a carbon fiber mat. You can see the interwoven white lines in here. That's aluminum that's interwoven in there. Creates an electrical current path that actually explodes and blows the paint away. We'll talk about paint more in a minute. So, non-conductive composites, fiberglass, Kevlar, that sort of stuff, can't carry electrical current flow. So if we don't protect them, what happens is they get punctured and we get an attachment, something underneath there, and it's what's called current flashover, and it explodes the part. All right? Carbon fiber composites, about 1,000 times as conductive as aluminum. But again, neither one of these are conductive enough by themselves to carry electrical current flow. So we have to be able to protect them. And typically we protect the outer layer and try to prevent that current from propagating into the part. Because in the case of carbon fiber, as we'll see in a minute, if current drives into that part and starts expanding out, because that part's not homogeneous like aluminum. It's not all made up at the same. It has a bunch of layers with adhesive in between those layers. So you get delamination, but more than that, as current flows through that part, it burns that resin up, and that burning of that resin creates gas, and then that gas has to have some place to go. And it expands and explodes apart. So, lightning produces damage to conductive skins basically by driving a bunch of electrical current into it, resulting in large amounts of heat transfers, thousands of degrees in a very, very short period of time. That heat burns it up, and that burning effect creates gas, and then you have gas and shock wave effects that blow the part apart. So, how do we protect it? We make it look like metal. That's how we protect it. So we have to improve the electrical conductivity on the outer surface. We can't stand for it to be 1,000 times as conductive. We have to make it more conductive. So we put a material on the outside, either that expanded metal foil or that ALS material that allows for the majority of the current to stay on the surface. And as long as I can keep that current on the surface of that part, and not drive into it, not create an outgas, not cause explosive effects, then I can minimize the effect of the strike. And by doing that, we have what's called arc root disbursement. And arc root disbursement means when the arc comes down and attaches to that surface, and that's what we call the lightning channel, is the arc root. Just like an arc welder, if you're in school and you did welding, right where that arc attaches to the surface, that's the arc root. And if I can spread that arc root out over a large area, just like we talked about multiple bonding straps, just like we talked about with electrical bonding of equipment, I reduce the current density in one area, I reduce the damage. So, we try to determine the arc root by conductivity of the outer layer, but also by surfacing and paint. And paint and surface coatings become extremely critical in regard to lightning protection of composites. If you put paint on the outside of that surface, it isolates that conductive material, thereby causing the arc to concentrate in one particular area. Drives the current into the part, that current's under pressure, it outgasses, it explodes. If you think back to that analogy I gave with an arc root, if I have a surface, a metal surface, and if you guys ever did any welding or anything, when you strike that arc root, you have trouble getting that guy to flow because it wants to bounce around and stick multiple places, or at least it did with me. Okay? But if I paint that surface a little bit and create a nice little channel, I isolate that, man, I can strike that baby and lay a bead right down through there. Same thing happens here. If I isolate that channel, okay, or if I isolate that surface, then that channel's still going to strike. It's just going to hit in one spot. So this is an analogy of that. The channel comes down, and when that lightning's impinging on that surface with a thin coating, there's all kinds of little streamers that are affected from that, either that expanded metal or that ALS, and they're all screaming, "Pick me, teacher, pick me." So the channel comes down, it spreads out very fast. But if I put too much paint on that surface, lightning's still going to strike it, okay? Remember, I don't have something I can pull the switch and say, I don't want that lightning channel to strike me. I either design it properly or I don't. So if I put too much paint on there, I concentrate the arc, and it drives it into the surface. The perfect analogy that I always use for this is I have 5 daughters, okay? The Lord's got a funny sense of humor, I know. But my number 3 daughter, okay, had a waterbed, and we had an upstairs. So that waterbed's a king-size waterbed at 8-something pounds a gallon. If you think about the weight of a king-size waterbed and all that water in there, it's tremendous. But if you look underneath there, there's some plywood boards and then some braces. And those braces effectively distribute that weight around that entire surface so that any one spot's not holding all of it. But now imagine if I lifted that waterbed up and could somehow manage to balance it on a broomstick of 1-inch diameter. She's sleeping downstairs because none of that floor couldn't handle that high amount of concentration of weight in one spot. It would destroy it structurally and collapse the floor. Same sort of analogy here. When I drive that current into a very small spot on that structure, it drives into it, spreads out, it expands out. So we went and ran a bunch of tests because there are composite structures in all the lightning zones on our airplane. Some of them are critical due to what's underneath it, whether it's electrical power, FADEC wiring, fuel lines, whatever. Some of them are critical due to the function they perform, like stabilizer, elevators, rudders, whatever. So they're all critical. Citation 10, everywhere you see that blue primer, it's a composite structure. It's all over the airplane. Okay. So we went and ran a bunch of tests in which we looked at various stack-ups of carbon fiber with Kevlar, like it's on the belly fairings, carbon fiber and carbon fiber with honeycomb, like on the engine nacelle. And we ran a bunch of tests and we came up with some guidelines on how thick that paint could be. So as a result of that, okay, we say that the paint thickness on these surfaces, if it's not controlled, you can't certify. If it is controlled, okay, not only can you certify it, but you can maintain the protection. If you don't control it, you can't maintain the protection. Okay? So the requirements for this particular 750, XL, and all of those are contained within the maintenance manual of section 20-3101 for all models. There's a picture of the airplane in there, identifies all the composite structures, and gives you the requirements for paint thickness on those surfaces. For legacy aircraft, only the ones with E-glass radomes have a paint thickness requirement on them. There's a couple of reasons for that. Number one, we don't use very many composites on those surfaces. And number two, they were designed and built before the rule came out. But you should control the paint thickness on those too, if for nothing else, for weight. Okay. So anyway, conclusion. The most important aspects of protection of lightning are electrical bonding of equipment to structure. A good electrical bond will drive lots and lots of advantages in regard to conductivity and surface density or current density. With the larger the surface, the lower the current density, the lower the impedance is. Proper design of current pass, i.e. whether it's rivets, bonding straps, screws, whatever, we have to make sure we have enough current flow pass in there. Bonding straps have to be sized properly. And in regard to composite structures, it's critical to electrically bond them correctly, but also to control the paint thickness. Okay, I kind of went through all of that really quickly. I know a lot of you have probably raised more questions than answers. However, there's a few things just to concentrate on. Number one, lightning strikes our airplanes, not on a real regular basis, but they certainly strike them. Okay. If we don't maintain the protections on those airplanes, then we can't guarantee the safety to our customer. So it's critical. We have a tendency not to think about bad things till they happen, and we want to make sure that when bad things do happen, like getting struck by lightning, the aircraft is not only designed right, but is maintained. Thank you.